Diamonds are famously the hardest natural material on Earth. But what if there was something even harder? A substance not born deep within our planet, but forged in the chaos of cosmic collisions. Today, we're talking about a mysterious, ultra-durable gem found inside meteorites, a material called Lonsdaleite, and how scientists are finally unlocking its secrets to spark a revolution in materials science. The story begins not on Earth, but in the vastness of space. Imagine a meteorite containing graphite, the same soft, gray stuff in your pencils, speeding through the void. When this meteorite slams into a planet, the incredible heat and pressure of the impact can do something amazing. It transforms that soft graphite into diamond. But this isn't the diamond you see in a jewelry store. The carbon atoms in graphite are arranged in a hexagonal sheet. Under the shock of impact, they don't have time to rearrange into the familiar cubic structure of a normal diamond. Instead, they snap into a hexagonal diamond structure, a direct inheritance from the graphite they once were. This is Lonsdaleite. This unique hexagonal crystal lattice is the secret to its power. While a typical diamond's atoms are like a perfectly stacked pile of oranges, Lonsdaleite's atoms form a different pattern, and this subtle shift is predicted to make it significantly harder. The first real proof of this hexagonal diamond appeared in 1967. Scientists were analyzing the debris from the Canyon Diablo meteorite, the very one that blasted the famous meteor crater into the Arizona desert. Tucked away in the wreckage, they found microscopic crystals of this new carbon form. They named it Lonsdaleite, in honor of pioneering crystallographer Dame Kathleen Lonsdale. This was it, the first concrete evidence that a diamond harder than Earth's could exist, and its origins were literally extraterrestrial. For decades, Lonsdaleite remained a mystery. The samples were tiny, impure, and hard to study. Some scientists even wondered if it was a real, distinct material or just a flawed version of regular diamond. But further clues came from a rare type of meteorite called uralites, believed to be fragments from the mantle of a long-lost dwarf planet. These meteorites contained Lonsdaleite, formed during a catastrophic collision about 4.5 billion years ago, providing more compelling evidence for this strange, alien diamond. So, how do you make something that requires the force of a planetary collision? That's the puzzle materials scientists have been trying to solve for years. Recreating the violent, high-pressure, high-temperature environment of a meteorite impact in a lab is incredibly difficult. Early attempts to just squeeze and heat graphite only produced tiny, impure particles, which fueled the skepticism. But science rarely gives up. A major breakthrough came in 2022. A team of researchers studying those uralite meteorites proposed a new formation process. They suggested the hexagonal diamonds didn't form from pure shock alone, but from a supercritical fluid at high temperature and moderate pressure. Think of it like a form of chemical vapor deposition, where you grow a crystal from a gas. This gave scientists a new, more manageable recipe to follow. And it worked. Building on this new understanding, labs started reporting success. In July 2025, a landmark paper was published in the journal Nature. Chinese researchers announced they had created high-purity Lonsdaleite crystals of a significant size. By applying precisely controlled high pressure and temperature to ultra-pure graphite, they produced hexagonal diamonds large enough for detailed analysis. This was the definitive proof that Lonsdaleite was stable and could be made on Earth. Another team refined the process even further, using a device called a diamond anvil cell to squash and heat purified graphite, forcing the atoms into that characteristic hexagonal pattern. Their results were astounding. The synthetic Lonsdaleite they created was confirmed to be at least 40% harder than natural diamond. The theoretical predictions were no longer just theory. So what makes this hexagonal shape so much stronger? It all comes down to the atomic structure. Both regular diamond and Lonsdaleite are made of pure carbon atoms, linked by incredibly strong bonds. But the arrangement is everything. In a regular cubic diamond, the atoms are arranged in a way that creates planes of weakness. Think of it like a block of wood. It's much easier to split it along the grain than against it. These planes are where a crack can start and propagate. Lonsdaleite's hexagonal structure, however, gets rid of these uniform weak planes. It's more like a tightly woven fabric, where forces are distributed more evenly, making it much harder to break or indent. For years, computer simulations predicted this would make Lonsdaleite up to 58% more resistant to pressure than cubic diamond. And now, the lab-grown samples are proving it. One research team reported their synthetic Lonsdaleite had a hardness of 155 gigapascals. To put that in perspective, a typical natural diamond clocks in around 100 gigapascals. This isn't just a minor improvement. It's a leap forward with massive implications for industry. The ability to manufacture a material significantly harder than diamond is a game changer. Let's start with manufacturing and machining. Imagine drill bits that can cut through the hardest rock or metal effortlessly, or saw blades that stay sharp for incredibly long periods. Industries like aerospace and automotive, which rely on precision machining of super-hard components, could see a revolution in efficiency and quality. We could machine materials like silicon carbide with far less wear and tear, leading to better brake discs, engine parts, and more. Then there's electronics. Diamonds are already used in high-end electronics to help dissipate heat because of their excellent thermal conductivity. Lonsdaleite is predicted to be even better, with superior thermal stability. This could allow us to build more powerful computer chips and electronic devices that can run hotter and faster without failing. The unique properties of Lonsdaleite might also find a home in the futuristic world of quantum computing, potentially forming the basis for new types of sensors and components. For aerospace and defense, where materials need to be lightweight but incredibly strong, Lonsdaleite is a dream come true. It could be used in high-stress components or as a wear-resistant coating for aircraft and spacecraft, protecting them from the extreme conditions of flight. Even the tools of science itself stand to benefit. The diamond anvil cells used to create these super high pressures are, of course, made of diamond. By making the anvils out of Lonsdaleite, scientists could push their experiments to even higher pressures, opening up whole new frontiers in materials science. Now, you might be wondering, will we see Lonsdaleite engagement rings anytime soon? While its cosmic origin story and superior hardness are certainly appealing, don't hold your breath. The cost and difficulty of growing large, clear, gem-quality crystals mean that for the foreseeable future, Lonsdaleite's true value is in high-tech applications, not high-end jewelry. Despite these incredible breakthroughs, we're still at the beginning of the Lonsdaleite story. The lab-grown samples are still small, often measured in micrometers, fractions of the width of a human hair. The next great challenge is scaling up production. Scientists need to figure out how to grow large, high-quality crystals that are big enough for industrial drill bits or electronic wafers. They also need to conduct more extensive testing to fully map out all of its properties: its mechanical strength, its thermal conductivity, its electrical resistance. But the path is clear. The journey of Lonsdaleite is a perfect example of how studying the cosmos can lead to world-changing discoveries right here on Earth. What started as a tiny, puzzling crystal found inside a rock that fell from the sky is now on the verge of transforming our technology. The secrets of the stars are being unlocked in our labs, paving the way for a future built on materials that are, quite literally, out of this world. The age of the unbreakable diamond has begun,